Yeah, thank you. No whales in the talk, unfortunately. That's a different talk altogether.
Yeah, that's great.
But I am going to talk about AI. Anyone been hearing about this recently? Because, it's all anyone seems to be talking about right now. But I'm hoping that I'm going to give you a very different take on it, a very different perspective. Because most of what you hear about it comes from either people who are using machine learning and AI, or people who are machine learning engineers working at big companies who are very good technically, but maybe don't have a scientific background. Just to let you know more about my background, so I've, for 20 years, been both in computer science and biology, both departments at the university. So I actually have a scientific perspective on machine learning and AI. So most modern day AI and machine learning, and most people think chatbots when you say AI, but of course it's much more than that. Most of it is, at its heart, a very powerful prediction machine, right? It's a forecasting machine. And it's really surprising to me how far these prediction machines have managed to take us, right, and what they've been able to do. But there are limitations, and I'm going to show you that today, that you can use them to predict the next tokens, next words, or part of words. You can use them to predict, in an image, if you send in the pixels, what's in the image, cat, dog, and so on. That's fine for prediction. But what you can't use most of these for, unless they have causal intelligence or use causal inference, is decision making. What happens if you want to change an outcome, not just forecast an outcome? But it's not the story we're being told, is it? Right? The story that we're being told is, well, if you have better data, if you have more data, if you have bigger, better models, then you'll be able to solve any problem. It's not the case. And I'm going to show you that later with a scenario with just 3 variables in different ways. I'm going to take you back to the late 1990s, cool time. I think Matrix is in the cinema, and even cooler, machine learning is on the rise for the first time properly. Neural networks are now quite big, all the precursors to actually what's being used to make modern day AI, just with more computer, more data now. So what happened was people wanted to make use of it. And a hospital actually decided to commission an AI and basically train this amazing neural network on decades of data from different hospitals. Really great data, great model. And what happened is, actually, this is giving it away too much. What happens actually is that it was designed to show for someone coming into the hospital whether they should be admitted to ICU, and actually what it was doing was predicting their mortality risk. And it did this really, really incredibly well, and they were really pleased with it. Great accuracy and everything. And someone would come in, for example, with suspected pneumonia, and they would ask the model what to do. So imagine a guy, late 1990s, comes into the hospital and he has suspected pneumonia and he has asthma, really bad asthma, and he's struggling to breathe. And computer says his mortality risk is really low, right? So it would suggest send him home. But of course, the doctors don't do that. They send him into ICU and they give him really extensive treatment. Now, the model's right. He survives, right? Because the doctors did the right thing. They didn't listen to the model. And that was a problem in that the AI did the right thing. It did what it was told. It was told to predict the mortality, and it did. Because if you go in with asthma and suspected pneumonia, you'll be treated so well and admitted to ICU that you will have a higher chance of survival. But what it didn't do is understand, right? It can predict, it cannot understand. It misses this line here. I'm going to show you lots of these causal diagrams, right? Basically, each of these is a variable, a piece of data. A line between is cause and effect potential. And this here is asthma, basically would increase mortality, but it's lower because they were admitted to ICU, right? So it didn't know this pattern. All it cared about, it was just in service to this outcome. So what I want to show you today, basically, is that predicting an outcome is not the same, it's just banging all over the place, is not the same as predicting an outcome given you've made and taken an action or an intervention to change that outcome. So if you use an AI or machine learning to tell you, here's what you do to change the outcome, that AI machine learning cannot be a predictive algorithm. It needs to have causal intelligence. It needs to be a causal algorithm. By the way, like the kind of algorithms we do at Causa, the kind of algorithms I do in science because I can't do experiments. That's what we do. So we're in the predictive era. How can I stop this banging about? What am I doing? I feel it's... I'm gonna put it in here. There we go. I feel like I'm singing now, though. Oh, it feels like an Oasis position. So yeah, in this predictive era, like AI and machine learning got really good at just one thing. And this is the one thing it's good at, which is predicting, or forecasting is another way of saying this. But it only can do that if nothing changes. So with large language models, so ChatGPT, Gemini, and so on, they forecast the next token, which is word or part of a word, and they do it one word at a time. Right? They don't know what they're going to say, they just do it one word at a time. So in the models of language, predictive models of language, they're not models of the world. They're different things, and I'm going to demonstrate that in a minute. There's, of course, lots of other machine learning and AI, looking at it. I have a business as well where we're doing stuff with computer vision. So you take in pixels and predict something in an image. You might predict or forecast demand, fraud, risk, churn. It's fine for all these kinds of things if you're just interested in prediction. The problem comes when you use it for decision making, and that's what I'm interested in. It's what most businesses are interested in, and in science, we're interested in why questions, normally. Certainly in ecology we are. The problem is, none of this is scientific, right? There's no why to it. As I've shown you before, the algorithm doesn't understand what's going on. It's just a servant to the outcome. And you can predict outcomes really well with a very bad model of the world, right? And what I mean by that is I always see modern day AI and machine learning as this kind of data blender, right? You shove a load of data in, just as much as you can. You blend it up, and it finds a way of getting to the outcome, the prediction, no matter the mix, right? And it doesn't care about how it mixes up in there. It can have some bizarre, bonkers, correlative view of the world in there that doesn't represent the patterns of cause and effect of what happens when you take action in the world. It doesn't need to. What it means is it's great for predicting the outcome. It's terrible for saying, well, what can I do? What can I change here to be able to get to the outcome, right? What can I change to get to the outcome I want? It doesn't know, because it's just blended it up in a way that doesn't make sense. That is all modern day predictive AI and machine learning. That's not causal. I recommend reading thebullshitmachines.com. It's a very good read. It's the best read I've read on large language models. Again, no one from Anthropic here. No. They're quite good. They've got quite far. They're good for helping with programming, copy, chatbots. I think that's about where it ends, really. But definitely not for decision making again. And they are also predictive. I don't think that's a limitation of them necessarily for what they do. But remember, they are models of language, not the world. The way they work, just really briefly, is, and this is very abstract, right? They take in words, might be the cat, right? And you send in to this, basically what you do is you turn it into a vector of numbers. The more similar the vectors of numbers, the more similar the words, so it already knows that. It goes into a transformer, which is essentially a very, very big equation, mathematical equation, right? Where it's learned the parameters of the equation, spits out another vector that turns into a word, right? And then it takes the next word, so the cat, the next word maybe sat. It adds that on, and it puts the cat sat into it, goes through the equation again, and it predicts the next word. And it does that one word at a time, right? That's how they work. Now, just to prove that they are prediction machines and they do not understand anything they're saying, this has been fixed in the latest version. Anytime you find a problem with them, Anthropic's like, let's put that in the prompt in. But as of like Claude Sonnet 4.6 Max, not pretty recent, this works. So you say to it, a boy and his father are in a car accident. At the hospital, the surgeon, who is the boy's father, says, I cannot operate on him. He's my son. What relation is the surgeon to the boy? The surgeon, who is the boy's father, right? I've given it the answer in the question, and it says his mother, right? The reason it does this is because it has no idea what you're saying. It doesn't understand the sentence. What it's doing is it's taking these words, turning them into vectors, putting them into here, and it's predicting the most likely answers. Now, in the training data, there is lots of gender bias kind of tests in it. And in that case, it doesn't say this line, and instead the father dies, right? The answer is the mother. because you have some people being, I don't know, the father died, who's the surgeon? And of course, it's a mother. So this is from like the 60s or something. But it's in the training data, right? And so it's learned that when you tend to see these words, you tend to have these words afterwards. It finds what the most statistically likely next word is, and then it does the next statistically most likely word. Right? Doesn't know what it's saying. And the problem with the kind of model, and it's not just large language models, any AI machine learning model that's not causal, they drown in correlations, right? And this goes for statistical models in science as well. A model that predicts perfectly, by the way, can tell you completely the wrong thing. A model, I'm going to show you this in a second, a model that cannot predict anything at all can tell you the right thing. So this whole idea that prediction equals decision-making is false. Just like the way correlation does not imply causation, predictive power does not imply causation either. But although most people understand that correlation thing, when I go into businesses, most data scientists don't understand the prediction thing for some reason. Now, there's lots of reasons you get correlations that are not causation. Of course, one that most people, at least in science and data science, know about is confounding. In science, this is often misunderstood. I had to write a paper on this recently, but one example of this might be, ice cream sales and shark attacks go up and down at the same time, but not because one causes it. Eating ice cream doesn't make you tastier to sharks. It's just that, when it's sunny, you tend to be having ice cream more, you tend to be in the water more. Just to show an example. That's one reason, but really we should be talking about confounding paths. Not confounding variables. I'm not going to go into this in any kind of a detail. I do want to say this over here is not confounding. This is what I find in science people confuse confounding for. You want to know the effect of X on Y, but A is also a cause of Y. You need to control for it. No, you don't. I can show you that in a minute. Biggest problem, though, in machine learning isn't confounding, because they're shoving all the data they can in. By the way, I should say that in a non-causal model, predictive model, if you include a variable in it, you are controlling for that variable. Not the case in the kind of structural causal models we use, but yes, the case in any other kind of model. You include it in the model, you're controlling for it, in the way that you would control for it in an experiment if you were holding it constant, right? Okay, but the problem is not these, it's bad controls. There are things you should absolutely not control for, else you completely cause it to give the wrong result. These are bad controls. And modern AI is full of them. Now, I'm just putting this in here in case there's any data scientists, because often when I talk to data scientists about this, they say, we've got the solution, explainable AI, but it's not the solution at all. Explainable AI does a completely different thing. It's not a make your model causal technique. It's a technique to show you what your model is doing. And when you see what your model is doing, you can see it's completely wrong. That's what explainable AI is. I don't really see a use case for it, actually. Okay, I'm going to show you this. Hopefully you can see that okay. So, whipped up an app. Thanks, Claude. But what I've done here, right, I'm going to talk you through it. So basically, I'm going to show you some examples with these causal diagrams, but I'm going to keep it really simple. Remember, I promised you with just 3 variables and different patterns of cause and effect, I can prove that no matter how much data you have, how big your algorithm is, and how good your data is, it cannot solve the problem, right? Now, I want to know, A is a lever I have. It's something I can do in the world, right? Change a price in a business, right? Or do treatment in medicine or something. C is the outcome, profit, health status, something like that. In this case, we've got roadblock protests, public awareness, for example, right? Now, I create a simulation model as a ground truth in this that follows this causal structure, right? So if I increase A, B goes up. If B goes up, C goes up. Simple, right? We can see what's going on. Even the most advanced AI with us, I can give it billions of data points. It doesn't matter. It will get this wrong. You'll see. Okay, so I know the ground truth in the real world, which I've simulated. And this is what most data scientists would do. They would say, well, we would normally do something called make, but to make it easier, you put actual C, which is the outcome, and the predicted C, again, predicted outcome. And if it's along a diagonal line like this, everything's great. It means it's predicting really well, right? So the model's predicting really well. And that's normally where we'd stop and say, that's a good model. Okay, but we want to use it for decision making, not prediction, remember? So when I increase A, we know what we expect to happen to C. Increasing A increases B, increases C. So C should go up when I increase A. So this is A, this is what happens in our simulation. This is what the model fitted to loads of data, and the best model fitted to loads of data does. Watch this. Oh, it does nothing, right? Predicts really well because it predicts just using B. And it says, well, B is downstream of A. I don't need A anymore. And it actually stops using A information from A. But you can't do that. In the models that we use, we actually get it to learn the causal structure. So it would know, it would get the predictions right, and it would know shift in A, shift C as well, via B. Let's look at another one. This one's even more nuts. You can ask me to explain this later, but it's hard to be intuitive about. A directly causes C, right? Directly increasing A will increase C. Pretty standard, simple, right? But actually, if A goes up, B goes down, and if C goes up, B goes down, right? It doesn't matter, it's just up there, it's not like causing either of them or anything, right? But again, I'm just assuming here we're doing the standard thing of shoving all the data that we have into the model. So we shove A and B in and say predict C. Fantastic, right? Does well again, it's on the diagonal. Predicting really well. What happens again? Let's see, this should work now, right? Oh, whoops, it's now going the wrong way. I see this all the time in business. It's telling you to do the wrong thing now, the opposite thing to what you should be doing. This is called a collider. These are really simple structures, but when you start doing this in the real world, they're not as simple as this, not as obvious. There's loads more I could show, but I want to show you. This is the one I showed you earlier where I said, now in this case, it's not a confounder, right? You don't need to control for Z. In this situation, we do control for it, and we can see it predicts really well, and there's no harm in controlling for it, right? Now we do get the right result, and it predicts well. Because there's no what we'd call a backdoor path. There's no non-causal pathway from A to C. But now watch this. Say that we didn't include Z. And we say, oh, you know, it's a confounder, it's a problem. Yeah, look at the predictions, right? We didn't include Z, and now our predictions are completely off. They should be along this diagonal. And the reason for that is that we've lost information about C that was in Z, right? Because it goes in a different direction to A. It's terrible for prediction, but watch this. Fantastic for decision making. We know the effect of A on C doesn't matter. It's not something you need to control for. Controlling for it increases precision, does not change, sorry, the accuracy does not change the precision. Okay, there's more there, but we've got limited time. So I want to go, again, what we do is apply this to business, but I've obviously done this in science a lot. So I've done it longer in science, so I have more examples in science. And in this situation, I want to show you some papers where they've got it completely wrong in important ways. So in this situation, check how much time I've been. Do I need to finish? Yeah? No? I can keep going. Okay, so this paper came out during COVID, and it was actually used in France to make policy decisions. And this is basically a big statistical model, like a machine learning model. And what they do is they throw in loads of factors about people, and then they try to predict their risk of death due to COVID, right? No, but the problem is, again, it's not a causal model. And now you've got loads of variables. Now each of these factors and outcome have different good and bad controls depending on where they are in this causal structure. There's something that's a good control for one will be a bad control for another. It's called a table 2 fallacy, or sometimes mutual adjustment fallacy. Here's a zoom in on it. Starts to look okay. Age groups, as you go up through the age groups, yeah, older is more at risk. Your men, slightly more at risk. More obese, more at risk. Oh, if you smoke, you're better off, right? Now, all of this is wrong. It's just that some of it is convincingly wrong. And this is what we find in business as well as science, right? It's very easy to do something and think that it got better because of the algorithm when actually it could have done better. But yeah, obviously smoking is not good. This was used for policy in France. It was then taken to court, and causal inference was used to show it was wrong. This is another paper just to pick one that's very easy. These are easy to pick on. This one was, by the way, one of the authors was the author of the book Bad Science, complaining about bad science. Ben Goldacre. And here, this study basically looks at loads of dietary factors, and it looks at basically people's aging, healthy aging. And in the paper, they actually say we control for BMI. Now, do you remember this? A causes B causes C. BMI is downstream of all of these things. Why did they control for it? There's no explanation. It's not a confounder. It's a bad control. There's lots more in this. Okay, it's been all very tidy so far, hasn't it? Look at this mess. This is an example from a client of ours of just one model. We're doing a few for them that all pieced together as well. When you do it for real, what happens in our algorithms, by the way, is you allow them to learn cause and effect relationships between all variables. In a standard predictive algorithm, no matter how complex they are, it assumes that causally all of the variables cause the outcome only, not each other. And all we do here is we relax those assumptions and say, allow the algorithm to learn a relationship between all the variables. Now it can learn stuff. So this doesn't have to be exactly right. What you need is to say there's a potential for a cause and effect here, and then the algorithm is allowed to learn it if it exists, right? And so we map this out with them using domain knowledge. Also, experiments can be done to when parts of the graph you're not sure about, and so on. Oh yeah, the X's are where if you use a predictive algorithm, these are bad controls, but not in ours because we can put in anything we want because it knows the causal structure. So I'm just going to take you through, I'm nearly done now. A very simple example. Again, simulated data because I don't want to show real client data. This is an example of churn. Just very quickly, I'm going to whip through it. On the left is predictive algorithm. On the right is causal algorithm. All this is showing is both predict churn. By the way, those who don't speak business, churn is just like the probability of like someone giving up their subscription, right? Leaving, for example, opposite of attention. We both do really well at predicting, right? So we have a good idea who's likely to churn. Now, this is where there are two other parts to this. You don't just want to know who's likely to churn. You want to know what can you do about it, right? So can we reduce the price of their contract? Can we give them a discount? Can we do there's loads of other stuff you can do, right? And if you do the predictive algorithm, it gets a wrong answer. It actually tells you, for example, that a retention discount is always a bad thing, when actually the causal algorithm gets it right in the simulation data, it's a good thing. And again, it's because of these bad controls going on. And the third thing that you need to know is who's most likely to churn anyway, and who can you do something about. But not only that, of those, different people might respond better to different treatments, right? So this kind of stuff is the only way you can do precision medicine, by the way, as well, because you can't do it with experiments, because you need too many people. You have to use causal inference methods and observational data as well as experiments. But here as well, you want to know like who would respond to discount, who would respond to a different method, and so on. And when you put it all together, like most AI projects fail when they're deployed in business. And a lot of people are saying, well, that's because it probably is right that they're not asking the right questions, but also that the data aren't good enough. But I'm pretty sure that it's because most of the time businesses thrive on decisions, and you can't make decisions with predictive models very well, right? And so we found when we're actually using these models in the real world, we're actually making massive profit for companies. This is a small profit compared to another one we're working on. Okay, I am done. Thank you.
So then I want to start with question number one. Based on the examples you showed when the predictive models give their own answers and then businesses just kind of do it, what was the, I don't know, weirdest things that you can tell about the customers from Yorkshire, ideally, maybe not Yorkshire, but anywhere globally, that actually happened in real world, and when you showed them to them, they were like, oh my God, like what are we doing with our lives? Anything that you can really tell without getting, into any.
All our clients have been amazing, actually.
Of course. I mean, probably the ones that maybe not clients, but it doesn't matter. But any real stories, like what people actually do that is weird.
I mean, in business, I'm just going to talk kind of generally, and I think that in business, what we see is it's very hard to kind of get across to most kind of well-trained data scientists who've been doing it for a long time. This kind of stuff that some people have been doing it for kind of 20 years using predictive models to look at things like pricing or something like that. That's quite one we've been looking at a lot recently. But of course, if you're not isolating the effect of pricing on sales, for example, then you're going to be setting your prices wrong. And I've seen examples where, previous predictive models have said, I'm going to be careful. Lots of different sites across the UK raise prices on all and everything. And then when you get it more causal, it's like in some places prices should be higher, in some places they should be lower. And that's what this kind of does as well. It allows you to know these kind of treatment effects, basically. But in science, it's probably, I work in ecology, and there's all this stuff about brain size and what causes the evolution of big brains and things like that. And I just see people going around in circles about, and we added a new variable in and it changed results. We added another variable in and it changed results. And there's this thing about brain size. It's always changing what people think is causing it. It's like, well, we added in whether they eat fruit and it's changed it. But there's no discussion about like, well, should that be something you're adding in? Is it change results because it's a bad control? Or is it change the results because it's a good control that should have been in there? They're assuming it's a good control, presumably, otherwise it wouldn't be publishable. And so I just see, what I see is the wrong results. I see lots of people who are making wrong assertions in science. I see lots of people making bad decisions in business, but then going with it anyway and thinking the model's fine because maybe, the business is just doing well in other ways anyway.
Yeah, that's a very interesting point, and I see that a lot of people could do a lot of like mistakes with pricing, for example. But can I develop this topic? And correct me if I'm like thinking completely wrong here. But let's talk about like Uber pricing, for example, right? Quite lately, they moved to a new system where it's like an always variable pricing. I don't know what they use for it, but I could assume that Causal AI can really give me the best possible pricing map for whatever I sell, right? And essentially they will tell me, okay, this kind of group of people will buy if you sell them even 10x or 20x more expensive, and these people will not buy anyhow. So from the business perspective, like for pure numbers, right, it sounds like I'll get the biggest profit. But what about the other parts of it that are not like, purely about the numbers, about the profit? Again, the Uber example has so much controversy in this, the pricing model they have, where like different times of day, different times of places, the driver can earn like £1 when the company earns £19. Like ethical questions. I think right now, like in Europe, there's like even regulation against it are being developed and stuff like that. So how will Causal AI play in this area? Will you be like an evil genius, maximizing profits and or no? Like how what do you think about that?
So I don't like dynamic pricing. And we haven't done any of that. But definitely we're trying to help companies with profit. They wouldn't pay us otherwise, right? If we wanted to pay us. But I mean, you can see this working, this kind of stuff actually applies really well to NGOs. And what decision making about how they can raise, and when we're doing well enough, we actually do already have plans to do some packages that would make it quick to be able to do some good with it as well. Yeah, dynamic pricing is a completely different thing. They do use predictive algorithms there to predict what the price should be based on weather and things like that. This is more like you're gonna do lots of different things. Like so one of the things that this is great at is if you want to make more than one decision at once, right? If you wanted to, for example, experiment with price and say, I'll do an A/B test. I'll test this price versus that price. Well, what price are you testing? How does that interact with whether you've done capex on a building that you're trying to rent out? How does it interact with the size of the sales team? You can't know any of this from an experiment, for example, as well, right? And what this allows you to do is look at lots of different things together, like premiumization, whether you've added this and that and the other. And it's very easy to add something that will mess up this model, right? You can add like inquiry rates, for example. It's going to mess up the impact of price on sales. Your model will tell you completely wrong thing. And that's maybe not obvious, where, how many guests they've had, 3 guest passes they've had, it messes it up. And not obvious. So what I see is people just thinking you can throw in everything, and the more the better. And it's not the case. You end up with over-control bias, basically, in these models, and it's a problem.
All right, so any questions from the audience? Let's do with this. Yeah, with you.
Hi. So I've worked with an explainable AI startup 5 or 6 years ago that can work on any kind of time series data. So what I'm wondering about is, would you say that you're working towards predictable AI or explainable AI? And where do you want to go from there?
Yeah, so explainable AI will tell you what your algorithm is doing, regardless of whether it's predictive or causal. If it's a causal AI, you don't need explainable because it's explainable out of the box because you can say, for example, what is the effect of price on sales? What's the price of trials on sales? What's the you can know the effect of every variable and every other variable. You can also look at the graph and you can have it colored by what's and the thickness of the lines, and you can actually watch information move around it. So causal AI doesn't need explainable AI because it's more explainable than explainable AI already, and it also maps on to the real world process. Explainable AI is only useful for predictive AI in that respect.
Can I ask just one more bit?
Yeah.
One of the things I've seen with startups, but also in science, is that you have known knowns, known unknowns, unknown knowns, and unknown unknowns. Sorry if that doesn't make sense. But if there's something that's happening in a business, but you don't actually collect data on it, so if it's an unknown unknown, does that mean that there's a huge gap in knowledge that you can't predict whatsoever?
Sometimes.
Any way around it is what I'm going to guess.
Yes, sometimes. So this is one example of that. So basically, sometimes you might be a confounder, you don't have data on it, and what we normally do is you would have, most of the time you have known unknowns, and then what you can do is we would put Bayesian prior on it, but you can basically do like a sensitivity analysis to see how strong it has to be. What we also have is, I'll come to this in a second, and what we also have is we have experimental tests that you can do as well. So any bit that you're not sure about, we actually use something like an entropy measure to look at where on the graph can we get the most information from conducting an experiment, and what should that experiment be? So instead of just like testing the thing we want to test, so you test the best thing to learn the causal structure, because ultimately that's what you want to know, right? So publishing a paper on that soon. But also sometimes with the kinds of models we use, so sometimes like causal inference is done with predictive models by drawing these diagrams and choosing what to include and what not to include, right? You don't put in those bad controls. The problem with that is we've never found that it's as simple as that. The problem is that if you go back to those papers of COVID risk, for example, you would need a different model for each of those factors in the outcome, right? Because something that's a bad control for one is not for another. So you would actually need like 100 different models for each one, and you've no idea how they interact with each other. We actually have models where they can learn the causal structure instead. So it's not the same as a predictive model, which is like everything just goes into the outcome. And what that actually does is make it more robust to some bias. Like in this case, this was called like the obesity paradox. In this case, basically, there's an apparent paradox in data, right? Where the high BMI basically increases risk of death. Or basically, let's say actually obesity increases the risk of death, but also increases the risk of type 2 diabetes, which increases the risk of death. But they were finding the opposite result. They were finding that being obese seemed to be be protective if you had type 2 diabetes. It's because there was this thing lurking down here, right? So, it's basically a confounder on type 2 diabetes and risk of death. Becomes if you don't condition on it, becomes a collider on type 2 diabetes. Normal models, they suffer collider bias because even though you don't have the data on it, it's still a collider in the real world. But actually, structural causal models get the right result for reasons that I don't have time to go into. So yes, these kind of models can solve it. If you think it's there, you can do a variation test or do a prior on it. And other than that, you can do experiment. Because experiment will deal with unobserved latent confounding.
All right, thank you. So there were another question over here. Okay, let's go with you, and then the gentleman in the white shirt. Yep.
Can it sort of detect the gravity well of where that confounding you haven't noticed yet is and tell you what it should be? Or do you have to tell it, oh, actually I've found this. Is it what's causing this? Can it see these things where it should be working but isn't?
So you can see places, for example, where the effects. I guess the only way you can really do that is like we would always say, with these kind of algorithms, we always design them with experts, like the domain experts, and we always take the results back to the domain experts. And if they point out and say this bit is looking a bit dodgy, either in the diagram or in the results, that's where we can actually say, maybe now we can start to brainstorm if there's something else going on. if we can't think of anything, we probably need to do an experiment. And what we would do there is we would normally do this Bayesian adaptive experiments. It's not like an RCT, it's much smaller, quicker, still causal, but it tells you what to test essentially, where you say you use information from the fitted causal diagram basically, to know where is the best place to test, essentially to get the most information gain. But yeah, I mean, unobserved confounding is always a problem outside of experimental testing. But the approach that we go for is instead of doing an RCT or an A/B test where you just test one value of one thing against another value of it, the purpose of the test is to learn the causal structure instead. And now you get this much richer view. You can do more precision things, and I mean, I've got things on this too. I think that experiments are often very limited and often break the rules of experiments, of causality in experiments anyway, most RCTs.
Thank you. One more question?
Well, yeah, okay. So I think you've been a little bit unfair. You seem to have burnt the machine learning model and the AI, and actually really what I think you're saying is bad feature engineering produces bad model output.
No.
Okay.
No, maybe explain a bit more.
So I mean, you've got a slide earlier on that was looking at churn. So if we look at the two models you've got looking at predicting churn. And I think
it's based on this,
No, the next one on I think it was.
No, but this kind of diagram is what's used for it, yeah.
Yeah, sure, but if we go to the results, I can explain what my thinking is. So the next one is it where you've got here we go, we've got the drivers here. So you said the pure correlation model is basically saying the retention discount is acting in a way you would not expect.
Yeah.
But is this not because you use your features that you fed into the model in the first place as being actually after you've given the retention discount?
No, it's because bad controls are in there. So in the same, and it's not obvious what they are. It's because, like, for example, this one is the effect of price and sales, and you wouldn't think like if you included, X members and guests in there, you're going to mess the model up, but you do, and it's because there's basically colliders and mediators being controlled for and conditioned on in the model.
That's exactly my point. It's bad feature engineering that you've not created enough features that really encapsulate the system that's going on.
I mean, so the only way to select features to go into a model is with a causal diagram, because otherwise you will get the bias. The problem is the feature engineering has been done without causality in mind.
In that case, I agree with you. But you say, you've got to make sure you pull out the right features that properly encapsulate the system, and if you don't, then you win.
Yeah, exactly. So for example, if we go back to this, if you have a model and you feature engineer and you say, I want to know the effect of A on C, and you say in your feature engineering you're like, I'm going to include A and B in the model, you've fucked up your model.
Yeah, completely.
But I wouldn't call that feature engineering really, because most people that I see do feature engineering will be doing things like saying, they'll be using some, maybe BIC, AIC, or they'll be using, dropping out variables and seeing predictive power. A lot of the feature engineering I see is done on predictive power. And if you do it on predictive power, you'll get the wrong answer, because here, B is the most predictive variable of C. And so I think it's, I guess so back to what you said at the start, I don't think I'm being unfair, because I think in practice, the way that people do feature engineering is different from what you're saying. And what you're saying is they should do causal inference.
If we're saying that people do feature engineering badly, then we agree.
Well, I think most businesses we've been into, and these are some big businesses, have data science teams who in this situation would select A and B and put them both into the model, basically. They wouldn't draw out a causal diagram and put it in, or they would, as in this case, they might have more than one thing that they want to take action on, and they would have one model. And it's a predictive model. But of course you need more than one model if you have more than one thing you want to take action on, because as I showed, what's something that is, this table 2 fallacy, something that is a bad control for one of your action outcome pairs is a good control for another one of your action outcome pairs. That's the case on this one, for example. And it would have one model, and that one model they're trying to do the same thing. And no, it's not about feature engineering anymore. It's about the fact that if you do it With a predictive approach, you need two models, both feature engineered differently.
But in theory, if you have enough data with enough of these features that you have articulated on this slide, then the model will produce great results, irrespective of whether it understands anything to do with causality, because it will unwrap the causality through the data that you have reflecting that causality.
No, it wouldn't. So, it wouldn't. So in this case, for example, this B is just a bad control, right? So it's just the equivalent of choosing any of these X's here and including them in the model. And so here, it doesn't matter how much data I give it. It doesn't matter how big the algorithm is, it will never be able to learn the effective AMT, ever. And I can actually prove it with this simulation. You can try this.
If you give it A and B, it will figure out how to disentangle A and B.
It won't. That's what this shows. Look. So here, right, it predicts really well, but it doesn't matter like how much data you give it. It will never know the effective.
The model doesn't have B in that model, does it?
Yes, it does. Yeah. This model includes both A and B. So it's using both A and B. If it didn't have B, this would be correct. Because B is bad control. Because B blocks the flow of causal information from A to C. Because remember, like I said, with predictive algorithms, including a variable controls for that variable. If you're controlling when you control for a variable side, like what you're basically doing is you're saying, I'm holding my finger on it, it can't move, essentially. So A is wiggling about like crazy, but B is not moving. And so that's the problem with it. So I don't think it is feature engineering. And I think that no matter how big your algorithm or how much data you have, it will never be able to unfold even the simplest example here. Have a go at it in code.
On this challenge.
Sounds like a challenge.
Yeah. It is.
All right. Thank you for the questions. If you don't mind, I'll just finish off with the one very simple, non-technical question from me. But I'm genuinely curious, like ever since I met you, like with all of this, I'm just curious, why do we have these predictive LLM models so huge, so hyped up, like enormous, and causal AI is still like not as hyped up at all? Like, what do you think is the main reason here?
I think it's because, well, a few reasons. I think one is because with language we have more data. You can train on all the data on the internet, all the books. You can photograph copyrighted books and get people to do cheap labor to label and so on, right? So I think one of it is data. So it's something where you can use big algorithms to predict words fine. This, I think, it's becoming well known in science, but I think that the problem is as well, a lot of what's done in machine learning and AI is done by computer scientists who are not very scientifically trained, and so they do think that if you have these big models, then you're going to be able to learn anything with them. But really, they can if you allow them to learn these structures, but these aren't allowed to learn those structures, and that's the problem. And you can get quite far with it. Like these language models are great for what they do, but they just can't make decisions. So why do I think it? I think it's because it's a more scientific way of thinking, and you have to customize the models a lot more for the particular case. What's a good control, bad control for one business in one problem is different from what is a good control and bad control for another business in another problem. And so you can't just use loads of data in a big model, basically.
Well, thank you so much. That's the next question. Well, if you have more questions, you can find Dan here in the audience. We still have plenty of time for networking. And Dan, thank you so much once again. It's been amazing. Round of applause for Dan.